So today I'm reading from the Using SQLite by J.A. Krebich, and today's chapter is chapter 4, the SQL language. This chapter provides an overview of the structured query language, or SQL, although sometimes pronounced SQL. The official pronunciation is to name each letter as SQL. The SQL language is the main means of interacting with nearly all modern relational database systems. SQL provides commands to configure the tables, indexes, and other data structures within the database. SQL commands are also used to insert, update, and delete data records, as well as query those records to look up specific data values. All interaction with the relational database is done through the SQL language. This is true when interactively typing commands or when using the programming API. In all cases, data is stored, modified, and retrieved through SQL commands. Many times, people look through the list of API calls, making for functions that provides direct program access to the table or index data structures. Functions of this sort do not exist. The API is structured around preparing and issuing SQL commands to the database engine. If you want to query a table or insert a value using the API, you must create and execute the proper SQL command. If you want to do relational database programming, you must know SQL. Learning SQL. The goal of this chapter is to introduce you to all the major SQL commands and show some of the basic usage patterns. The first time you read through this chapter, don't feel you need to absorb everything at once. Get an idea of what structures the database supports and how they might be used. But don't feel that you need to memorize the details of every last command. For people just getting started, the most important commands For people just getting started, the most important commands are create table, insert, and select. This will let you create a table, insert some data into the table, and then query the data and display it. Once you get comfortable with those commands, you can start to look at the others in more depth. Feel free to refer back to this chapter or the command reference in Appendix C. The command reference provides detailed descriptions of each command, including some of the more advanced syntax that it isn't covered in this chapter. Always remember that SQL is a command language. It assumes you know what you are doing. If you are directly entering SQL commands through the SQLite 3 application, the program will not stop and ask for confirmation before processing dangerous or destructive commands. When entering commands by hand, it is always worth pausing and looking back at what you have typed before you hit return. If you are already reasonably familiar with the SQL language, it should be safe to skim the chapter. Much of the information here is on the SQL language in general, but there is some information about the specific dialect of SQL that SQLite recognizes. Again, Appendix C provides a reference to the specific SQL syntax used by SQLite. Brief background. Although the first official SQL specification was published in 1986 by the American National Standards Institute, or ANSI, the language traces its roots back to the early 1970s and the pioneering relational database work that was being done at IBM. Current SQL standards are ratified and published by the International Standards Organization (ISO). Although a new standard is published every few years, the last significant set of changes, the core language can be traced to the SQL 1999 standard, also known as SQL 3. Subsequent standards have mainly been concerned with storing and processing XML-based data. Overall, the evolution of SQL is firmly rooted in the practical aspects of database development, and in many cases, new standards only serve to ratify and standardize syntax or features that have been present in commercial database products for some time. The core of SQL is a declaration language. In a declarative language, you state what you want the results to be and allow the language processors to figure out how to deliver the desired results. Compare this to imperative languages such as C, Java, Perl, or Python, where each step of calculation or operation must be explicitly written out, leaving it up to the programmer to lead the program, step by step, to the correct conclusion. The first SQL standards were specifically designed to make the language approachable and usable by non-computer people, at least by 1980's definition of the term. This is one of the reasons why SQL commands tend to have somewhat English-like syntax, most SQL commands take the form verb subject. For example, create verb table subject, drop index update table table name. The almost English declarative nature of SQL has both advantages and disadvantages. Declarative languages tend to be simpler, especially for non programmers to understand. Once you get used to the general structure of the commands, the use of English keywords can make the syntax easier to remember. The fixed command structure also makes it much easier for the database engine to optimize queries and return data more efficiently. The predefined nature of declarative statements can sometimes feel a bit limited. However, especially in a command based language like SQL, where individual isolated commands are constructed and issued one at a time, if you require a query that doesn't fit into the processing order defined by select commands, you may find yourself having to patch together nested queries or temporary tables. This is especially true when the problem you're trying to solve is inherently non relational, and you're forced to jump through extra hoops to account for that. Despite its oddities and somewhat organic evolution, SQL is a powerful language with a surprisingly broad ability to express complex operations. Once you wrap your head around what makes SQL tick, you can often find moderately simple solutions to even the most off the beaten path problems. It can take some adjustment, however, especially if your primary experiences is with the imperative languages. Portability. SQL's biggest flaw is that the formal standardization has almost always followed common implementations. Almost every database product, including SQLite, has custom extensions and enhancements to the core language that help differentiate it from other products, or expose features or control systems that are not covered by the core SQL standard. Often, these enhancements are related to performance enhancements and can be difficult to ignore. While this less strict approach to language purity has allowed SQL to grow and evolve in very less practical ways, it means that the real world SQL probability portability is not all that practical. If you strictly limit yourself to standardized SQL syntax, you can achieve a moderate degree of portability, but normally this comes at the cost of lower performance and less data integrity. Generally, applications will write to the specific SQL dialect they are using and not worry about the cross database compatibility. If cross database compatibility is important to a specific application, the normal approach is to develop a core list of SQL commands required by the application with minor tweaks for each specific database product. SQLite makes an effort to follow the SQL standards as much as possible. SQLite will also recognize and correctly parse a number of non standard syntax conventions used by other popular databases. This can help with the portability issues. SQL is not without other issues, but considering its lineage, it is surprisingly well suited for the task at hand. Love it or hate it, it is the relational language of choice. And it's likely to be with us for a long time. General syntax. Before getting into specific commands in SQL, it is worth taking it's worth looking at the general language structure. Like most languages, SQL has fairly complete expression syntax that can be used to define command parameters. A more detailed description of the expression support can be found in Appendix D. Basic syntax. SQL consists of a number of different commands such as create table or insert. These commands are issued and processed one at a time. Each command implements a different action or feature of the database system. Although it is customary to use all capital letters for SQL commands and keywords, SQL is a case sensitive language. All commands and keywords are case insensitive, as are identifiers such as table names and column names. Identifiers must be given as literals. If necessary, identifiers can be enclosed in the standards compliant double quotes to allow the inclusion of spaces or other non standard characters in an identifier. SQLite also allows identifiers to be enclosed in square brackets or backticks for compatibility with other popular database products. SQLite reserves the use of any identifier that uses SQLite as a prefix. SQL is a whitespace insensitive, including line breaks. Individual statements are separated by a semicolon. If you're using an interactive application such as SQLite, such as the SQLite 3 command line tool, then you will need to use a semicolon or to indicate the end of a statement. The semicolon is not strictly required for single statements, however, as it is properly a statement separator and not a statement terminator. When passing SQL commands into the programming API, the semicolon is not required unless you are passing more than one command statement within a single string. Single line comments start with a double dash and go to the end of the sequel. Also supports multi-line comments using the C command syntax. As with most languages, numeric literals are represented bare. Both integer 453 and real numbers 43.23 are recognized, as is exponent style scientific notation like 9.745 e to the power minus 6 in order to avoid ambiguities in the parser. SQLite requires that the decimal point is always represented as a period, regardless of the current internationalization setting. Unless otherwise specified, case insensitivity always applies to ASCII characters, that is, characters represented by values less than 128. Yeah, so I think we were at the basic syntax. So I'll start reading from the basic syntax again. SQL consists of a number of different commands such as create, table, or insert. These commands are issued and processed one at a time. Each command implements a different action or feature of the database system. Although it is customary to use all capital letters for SQL commands and keywords, SQL is a case insensitive language. All commands and keywords are case insensitive, as are identifiers such as table names and column names. Identifiers must be given as literals. If necessary, identifiers can be enclosed in the standards compliant double quotes to allow the inclusion of spaces or other non-standard characters in an identifier. SQLite also allows identifiers to be enclosed in square brackets or backticks for compatibility with other popular database products. SQLite reserves the use of any identifier that uses SQLite underscore as a prefix. SQL is a whitespace insensitive, including like line breaks, individual statements are separated by a semicolon. To indicate the end of a statement. The semicolon is not strictly required for single statements, however, as it is properly a statement separator and not a statement terminator, when passing commands into the programming API, the semicolon is not required unless you are passing more than one command statement within a single string. Single line commands start with a double dash and go to the end of the line. SQL also supports multi-line commands using the C command syntax. As with most languages, numeric literals are represented bare. Both integer 453 and real rational numbers 43.23 are recognized, as is exponent style scientific notation like 9.745 e to the power minus 6. In order to avoid ambiguities in the parser, SQLite requires that decimal point is always represented as a period, regardless of the current internationalization setting. Text literals are enclosed in single quotes to represent a string literal that includes a single quote character. Use two single quotes in a row like publisher equals O'Reilly. C style backslash escapes are not part of the SQL standard and are not supported by SQLite. Blob literals or binary data can be represented as an X or capital X followed by string literal of hexadecimal characters. SQL statements and expressions frequently contain lists. A comma is used as the list separator. SQL does not allow for a trailing comma following the last item of a list. In general, expressions can be used any place a literal data value is allowed. Expressions can include both mathematical statements as well as functions. Function calling syntax is similar to most other computer languages, utilizing the name of the function followed by a list of parameters enclosed in parentheses. Expressions can be grouped into sub-expressions using parentheses. If an expression is evaluated in the context of a row, such as filtering expression, the value of a row element can be extracted by naming the column. You may have to qualify the column name with a table name or alias. If you are using cross-database queries, you may also have to specify which database you are referring to. The syntax is like database name, then table name, and column name. If no database name is given, it is assumed you are referring to the main database on the default connection. If the table name or alias is omitted, the system will make a best guess using the column name, but will return an error if the name is ambiguous. Three-valued logic. SQL allows any value to be assigned a null. A null is not a value in itself. SQLite actually implements it as a unique valueless type, but it is used as a marker or to flag to represent the unknown or missing data. The thought is that there are times when values for a specific row element may not be available or may not be applicable. A null may not be a value, but it can be assigned to data elements that normally have values and can therefore show up in expressions. The problem is that nulls don't interact well with other values. If a null expression represents if a null represent an unknown that might be possible values, how can we know that if the expression null greater than equal to 3 is true or false? To deal with this problem, SQL must employ a concept called three-valued logic, which is often abbreviated as TVL or 3VL and is more formally known as the ternary logic. 3VL essentially adds an unknown state to the familiar true-false Boolean logic system. So here are the truth tables for trivial operations, not and or. So true when not value is false, false becomes not value of true, null becomes null. True and false, true, false, and null. Mm, I don't get how it's basically trivial also dictates how comparisons work. For example, any quality check involving a null will evaluate to null. Okay. So I think if we have true null, then it will be null, true false, it is null. Oh, yeah, sorry, my bad. So it's like, so we have true, true. So it's like joining these two. True and false is false, true and null is null. False and true is false, false and false is false, false and null is also false. Null and true is null, false and null is false, and null. So basically, we are using the short circuiting here, like ignoring the null values. That's why only in case of so anything with false getting and with false it's always false, and same is for getting or with true, like you have true or null, that is true, it doesn't matter what the null value is. So I think that's a like a good approximation. And trivial also dictates how comparisons work involving a null will evaluate to null, including null um, equals null, remembering that null is not a value, it's a flag for the unknown. So the expression null is asking, does this unknown equal that unknown? The practical answer is that is unknown. It might, but it might not. Similar rules apply to create a chain, lesson, or other comparisons. If you're having trouble resolving any expression, just remember that a null marks an unknown or unresolved value. That is why the expression false and null is false, but true and null is null. In the case of first expression, the null can be replaced by either true or false without altering the expression result. That isn't true for the second expression, where the outcome is unknown, in other words, null, because the output depends on the unknown input. Yeah, that's what I think we assumed. So yeah, I think we'll cover till simple operators. So SQLite supports the following unary prefixes of operators, like minus, plus. These are just the sign of a value. Like minus operator flips the sign of the value, effectively multiplying it by minus 1.0. The plus operator is essentially a no-op, leaving a value with the same sign if previously had. It does not make any negative values positive. um, and as in the C language, the tilde operator performs bitwise inversion. The operator is not part of the SQL standard. The NOT operator reverses a Boolean expression using a 3VL. There are also a number of binary operators. They are listed here in descending precedence. String concatenation, this is the only string concatenation operator recognized by the SQL standard. Many other database products allow plus to be used for string concatenation, but SQLite does not. Plus, minus, star, and percent, standard arithmetic operators for addition, subtraction, multiplication, division, and modulus. The bitwise operator and shift high and shift low as found in C language, these operators are not part of the SQL standard. Comparison test operators, again just as in C language, we have less than or equal, greater than equal. These operators are subject to SQL's trivial regarding nulls. Equality test operators, both equals and equals equals will test for equality, while both not equals and uh, this greater than less than test for inequality. Being logic operators, these tests are subject to SQL's 3VL regarding nulls. Specifically, value is null will always return null. In like glob with glob match regular expression, these five keywords are logic operators returning true, false, or null state. See Appendix D for more specific on these operators. And or logical operators, again, they are subjected to SQL's 3VL. In addition to these basics, SQL supports a number of specific expression operations. For more information on these and any SQL specific expressions, see Appendix D. So that's what we are reading till today.